Hello students, today I am going to talk about very interesting molecule cis-1 dimethylcyclohexane. We know that this molecule is optically inactive, but the reason behind it is controversial because some YouTube teachers, sources, Google AI saying that it is due to plane of symmetry and some professor saying that it is because of the ring flipping. So what is the correct reason? We should understand it. And in this video, I am going to explain you the correct reason through three-dimensional molecular model. Before that, I would like to show you what Google is saying. When I ask Google why cis-1 dimethylcyclohexane is optically inactive, then it is saying that this is optically inactive because it is a meso-compound possessing an internal plane of symmetry that makes the molecule achiral. According to that statement, this molecule has internal plane of symmetry. And another reason, what it is saying, conformational equilibrium. So it is saying that chair conformations might temporarily appear chiral. The rapid interconversion between this chair conformation via ring flipping means the molecule exists in overall achiral balanced state, resulting in zero net optical rotation. So another statement is saying that this molecule exists as a enantiomer, and these enantiomers are interconvertible into each other. If I am a student, then I don't know which statement I should write. If I write internal plane of symmetry, then I will get 0 marks. But if I write conformational equilibrium, then I will get full marks. And in this video, I am going to explain you why this conformational equilibrium is the reason, or we can say that ring flipping is the reason for the optical inactivity of this compound, not the internal plane of symmetry. And I will show you this molecule doesn't have any plane of symmetry. Before going to that, I want to show you what ChatGPT is saying. When I said ChatGPT, cis-1 dimethylcyclohexane is optically inactive due to ring flipping, not due to plane of symmetry, then it is saying me no. Cis-1 dimethylcyclohexane is optically inactive due to internal plane of symmetry, not because of ring flipping. Again, I got confused. So what should I write in the paper? So, and what it is saying that the ring flipping actually does interconverts axial to equatorial, does not change RS, does not convert enantiomer. All these statements are 100% correct. There is no doubt about it. So what is actually happening? If all these statements are correct, then why the ring flipping causing it to convert into the another enantiomer, right? So I am going to explain you through the 3D model of this chair conformation of 1,2-dimethylcyclohexane what is actually happening because of the ring inversion. So first of all, we should know that cyclohexane we are writing in as a planar molecule, but it exists as a chair conformation. Now look at the cis-1 dimethylcyclohexane. For our clear understanding, I am labeling one methyl as a red color and another methyl as a green color. If you see this molecule and pass the plane through this, then you can say that this molecule has a plane of symmetry. But this is the wrong way because this molecule exists as a chair conformation. Now if you pass the plane, the same plane through this molecule, 1 to carbon-carbon bond and 1 for carbon-carbon bond, now you can see that you can't divide this molecule into two identical halves, and hence we can clearly say that this molecule doesn't have plane of symmetry. So our first question answer is that this molecule doesn't have plane of symmetry. So whatever ChatGPT or Google AI is saying is wrong, that this molecule has a plane of symmetry. This is wrong. Now we will see the three-dimensional model of this molecule for our better understanding. So this is the three-dimensional representation of cis-1 dimethylcyclohexane. You can see that this is the axial methyl group and this is the equatorial methyl group. Now you can also notice that the axial groups are always looks vertical, whether it is in the downward position or in the upward position, always looks perpendicular, but the equatorial groups are always tilted at some angle. Now you can see the proper angle of this molecule. You can see that this equatorial bond methyl group is somehow tilted, but this one is perpendicular to this carbon. Okay, now if you pass this XYZ axis of this molecule, then you can see that this is the x-axis, this one is the y-axis, this is z-axis. None of the plane can divide this molecule into two identical halves. So you can't divide this molecule into two identical halves either by passing x-axis, y-axis or z-axis. So now it is clear that this molecule doesn't have any plane of symmetry. Such molecules undergo ring flipping at room temperature, in which axial methyl group is converted into equatorial and equatorial methyl group converted into axial methyl group without changing the configuration. You can see that carbon number 1 has R configuration here and here also, and here carbon number 2 has S configuration, in here is also S configuration. So remember that ring flipping doesn't change the configuration. It only converts axial to equatorial and equatorial to axial. Now it is clear that there is no change in the configuration. So what is happening now? The energy of conformer A and conformer B are same because of the axial methyl group. Both have 1,3 diaxial interactions, and 1,3 diaxial interactions accounts for 1.8 kilocalorie per mole energy strain, and it is same in both the cases. So both conformers A and B are equivalent in energy and stability, due to which they exist in a 50-50 of mixture. Now let's see the three-dimensional structure of conformer B, and then we will think what is the relationship between A and B. This is the 3D model of conformer B. This is the carbon number 1, which has methyl equatorial methyl group labeled as a red color, and this is the carbon number 2, which has green methyl group. Now you can see the better view of this molecule. So now question comes, what is the relationship between conformer A and conformer B? To check this relationship, I have to rotate the conformer B around y-axis 120-degree angle. So let's see in the 3D view. Now I am going to rotate this molecule 120-degree around y-axis in the clockwise direction, and let's see what we will get. So this is 60-degree and this is 120-degree. Now let me align it properly. Okay. Now you can see that after 120-degree rotation, conformer B can be written in this form also. And in the 3D view, you can see that conformer B and conformer A are nothing but mirror images of each other, and these mirror images are non-superimposable, due to which we can say that conformer A and B are enantiomers, which are non-separable due to rapid interconversion. So due to rapid interconversion of these one conformer to another at room temperature, we can't separate them, and they are enantiomer, and hence one conformer cancelling the optical activity of the other, and hence the molecule is optically inactive. So what is the conclusion from the whole discussion is that cis-1,2 dimethylcyclohexane is optically inactive, not because of plane of symmetry, but because of two enantiomeric conformations, these A and B, which interconvert rapidly via ring flipping at normal temperature. Okay, now it is clear. Now we are going to focus, should we call this compound achiral or meso? So achiral compound is the compound has no chiral centers and has superimposable mirror images. But meso compound, the most common definition for the meso compounds are those achiral compounds have stereocenters, but achirality is due to plane of symmetry or center of symmetry. If you apply this definition, then it doesn't match to the cis-1,2 dimethylcyclohexane, because 1,2 dimethylcyclohexane doesn't have any plane of symmetry, right? But it is achiral. So what is the actual definition of meso compounds? So according to IUPAC Gold Book, meso compound defined as a term for the achiral members of set of diastereomers, which also includes one or more chiral members. So in simple way, let's take tartaric acid. It has two chiral center, and this compound must show 4 stereoisomers, but it's showing only 3 stereoisomers, and one of them is meso compound, but 2 are enantiomers, and in that case we are saying one which is not showing the optical activity, what we are saying meso compound, right? That we are calling meso compound. So here similarly we should call cis-1,2 dimethylcyclohexane as a meso compound. Why? Because 1,2 dimethylcyclohexane exists as two diastereomers, cis and trans forms, and trans isomers is chiral, right? Trans isomer is chiral. I will make another video on trans one. Whereas the cis isomer is achiral, as previously discussed. Okay, we have already discussed. Hence, the cis isomer meets the definition according to IUPAC Gold. It is classified as a meso compound. So it is meso compound. If there is an option that you should call it Achiral or meso-compound, then you must say it is meso-compound. I think everything is clear about this cis-1 dimethylcyclohexane.
This is all about cis-1 dimethylcyclohexane, and I hope you like this video. And comment your difficult chemistry topic. I will make a video explaining them step by step. See you, take care, bye bye.